Hi, Ishan. I had a query.
Sorry?
I want to ask something.
Yeah.
So, the lecture notes, will we be provided with them as well? Because we would be making them, of course, but sometimes we miss some things.
Yeah, I will share you the slides that will go through in the lecture itself. And besides that, a Kritika module has also been shared to you on the group, right?
Oh, that's perfect. Are the modules the same ones that were on GitHub?
Yeah, they are the same, and they have covered almost all the topics in very detail. So you won't be needing anything besides that.
Oh, yeah, that's perfect. Actually, I was studying from them earlier and was doing some mathematics out of them, so I was wondering if they're the same.
Yeah, yeah, they're the same.
Uh, we start at 5 exact, right?
Yeah.
Okay. So I haven't attended any other summer schools earlier, but is Kritika like an annual event?
Sorry.
Is Kritika an annual event?
No, Kritika is the name of our club, and this learner space
On
is a
learner space, sorry. Yeah,
yeah,
yeah.
learner space is an annual event for it's like held by one of our clubs at IIT Bombay, but for Kritika we have opened it to everyone.
Hmm. Okay. Okay. And we will also be doing a bit of competition as well, right?
Sorry, you're not really audible.
Wait a minute, let me switch my mic. But we will also be doing a bit of competition, right?
No, it's not a competition. It's just a course like for people interested in learning astronomy. It's not really a competition.
No, no, computation, coding, Python,
Oh, sorry.
etc.
Yeah, yeah. There is a competition part to this learner space as well.
Okay, that's good. I just wanted to confirm. Great.
Actually, you'll be having like a short computational assignment after this module itself. My co-host like Aram will brief you about it after the session.
Oh, that's great. And for the doubts and queries, we can put them in the group, right?
Yeah, yeah. You can use the group, and you can also ask the speakers themselves.
Oh, perfect. Thank you.
Hello, am I audible?
Yes, yes.
Yes.
Okay.
Sorry.
Okay, we will start now. Hello everyone and welcome to the first module of the Fundamentals of Astronomy. I am Ishan and joining me is Aram. And today we will be discussing celestial mechanics and gravity. Let's look at our roadmap for today. We have broken the session down into 5 acts. I'll be taking you through the first 3. First, we'll look at the mathematical foundation, how computers calculate physics. Second, we'll look at the two-body problem, where we will derive Kepler's law from scratch. Third, we'll explore what happens when we add a third body to this third body and the system becomes chaotic. The mathematical foundation. Everything in celestial mechanics starts with a simple idea from Newton. Force equals mass times acceleration. By plugging in Newton's law of gravity, universal gravitation, we get this differential equation you see here. It looks elegant on paper, but if you want to know where a planet will be in like a million years from now, just writing the equation isn't enough. You have to solve it. There are two ways to approach this. The first is an analytical solution. This is a closed form mathematical equation. You plug in time and it gives you the exact coordinates. However, analytical solution really only exists for the simplest isolated systems. For almost everything in the real universe, we have to use numerical solutions. This means we have a computer approximate the answers, calculating it step by step. Let's start with the two-body problem. When exactly two massive objects interact through gravity alone, something very clean happens. They don't orbit each other the way most people picture it. One fixed, one moving. They actually both orbit their shared center of mass called the barycenter. Look at this animation. The heavy body traces a tiny wobble, while the lighter one swings in a wide arc. The barycenter sits between them, always closer to whichever one is heavier. For the Earth and Moon, that barycenter sits about 4,700 kilometers from Earth's center, which is inside Earth. So the Earth barely moves while the Moon swings wide. While for the Sun and Jupiter, though, Jupiter is so massive that the barycenter sits just outside the Sun's surface. The Sun itself traces a small but real orbit. That wobble, by the way, for a star moving slightly because of an unseen planet's gravitational pull is exactly how we detect exoplanets. We don't see the planet, we can't see the planet. We see the star itself moving. We're all familiar with the Kepler's three laws. Orbits are ellipses, planets sweep equal areas in equal times, period squared is proportional to the semi-major axis cube. Kepler found these empirically. He stared at Tycho Brahe's observational data for years and just pattern matched until these laws revealed themselves. But today, we're going to derive all three of them directly from Newton's equation of motion. No observations needed, just mathematics. To prove Kepler's law, we start with the basic equations of motions for a two-body system. We have mass 1 and mass 2, and the forces they exert on each other are equal and opposite. F12 is equal to minus F21. If we subtract their acceleration equation, we reduce the system to a one-body system. Single body problem. Define a new vector r as the distance between them. Mu here is just the reduced mass of the system. So we arrive at the equation mu d2r by dt square is equal to capital F. Now because the gravitational force is central, that is it acts straight along the radius, the torque on the system is zero. Zero torque means the angular component of acceleration completely disappears. So we can equate this term to be zero. This leaves us with the critical constant mu r squared d theta by dt is equal to c. Now if you look at it carefully, this c is just the angular momentum, which is constant because we have equated this equation to zero. We'll get back to this equation. Now we'll look at the total energy, which is just the kinetic energy plus the potential energy. Rewriting it in polar coordinates, our energy equation comes out to be half mu r dot square plus L square upon 2 mu r square plus the potential energy. We isolate the radial velocity to be equal to this term from this equation. Now, to find the shape of the orbit, we need the radius as a function of angle, not time. So we use the chain rule to combine equation 2.14 and equation 2.11. And after integration, we arrive at this equation. We then go on and substitute the potential energy to be minus g m1 m2 by r to then integrate it using proper methods to arrive at the equation r is equal to r naught upon 1 minus epsilon cos theta. This is the equation of a conic section in polar coordinates, where r naught is the semi-latus rectum, epsilon is the eccentricity of the conic, and theta is the angle from the line joining a focus and its perigee. This leaves us with 4 cases, but the one that we are interested is this one, because a planet bound to a star has negative total energy, so we need E less than 0. This leaves us with the equation being one of an ellipse. This is Kepler's first law. Moving on, we know from the above equation that L upon mu is equal to r square d theta by dt, which is basically a constant, right? And dA by dt, which is our aerial velocity, is c L upon mu, which is c r square d theta by dt, which is constant. So this is where our second law comes from. We can write the elemental area dA to be half r square theta, which upon integration leaves us with pi AB is equal to LT upon 2 mu. Upon substitution of constants, we get t square, which is the period, is equal to some constant times a cube. So this was our third law. Now that we have derived Kepler's 3 laws and also the equation of path for a two-body system, let's look at that in a simulation. This is a circular orbit, and we can also get an ellipse if we just manipulate the initial velocity like this one. You can basically get all the 4 cases that we discussed over here by just manipulating the initial conditions. The slide will be shared to you after the lecture, so you can just interact with this to see what initial conditions give you which of the following cases. Now, let's talk about 3 bodies. This is where things get very interesting, to say the least. After the elegance of the 2-body problem, the natural question is, can we do 3? This wasn't just mathematicians being curious. By the 1800s, accurate navigation across oceans depended on knowing the moon's exact position to calculate longitude. And the moon doesn't just orbit Earth in isolation. It's constantly being pulled by the sun at the same time. Earth, moon, sun, 3 bodies. So the question became pressing. If we can solve 2 gravitating bodies exactly and get perfect ellipses, can we not extend that 3? The greatest mathematicians of the era worked on it for decades. It really seemed that it was a matter of time before we come up with an actual solution. Then a Swedish king decided to put prize money on it, and the answer that came back changed mathematics forever. In 1888, King Oscar II of Sweden offered a formal prize for meaningful progress on the 3-body problem. Henry Poincare entered, and he won, but not in the way anyone expected. Poincare didn't just find a solution. He didn't find a solution. What he actually found was something far more important. He showed that in a 3-body system, tiny differences in starting conditions, positions changed by the smallest imaginable amount, can grow over time into completely different trajectories. The equations are deterministic. Given perfect initial conditions, the future is fixed. But in practice, no measurement is ever perfect. And in these systems, any imperfection gets amplified exponentially. His work didn't close the three body problem. It revealed that the problem was pointing at something much deeper. The three body problem became the birthplace of modern chaos theory. Here's what chaos actually means. Because people often confuse it with randomness. It's not random. The system is fully deterministic. Given perfect knowledge of every position and velocity, the future is fixed. Chaos means that any measurement uncertainty, however tiny, gets amplified exponentially until your prediction becomes meaningless. Alter the body's starting position by 0.1%, a fraction of a millimeter on planetary scales, and the long-term trajectory diverges completely. Let's look at a video to understand this better. The video that I'm about to show you is an overlap of three different simulations of the three-body problem, each with almost the exact same initial conditions. Yet, as you will see, all of them eventually go in their separate, chaotic ways. So this is the butterfly effect applied to celestial mechanics. And it's not just a simulation artifact. The system itself is chaotic, even in real universe, even with perfect physics. In 2009, a team ran thousands of supercomputer simulations of our solar system forward 5 billion years. In each one, they shifted Mercury's initial position by less than a single millimeter. In about 1% of those runs, which is a huge number, 1% for all those runs, that 1 millimeter difference cascaded into complete destabilization of the inner solar system. Mars in a new orbit, Mercury ejected, Venus colliding with Earth. 1% sounds small until you realize it means the long term stability of our solar system is a probability, not a guarantee. Now, here's the mathematical reason that there is no solution. For a planet orbiting one star, we had one differential equation. For three bodies, you have nine. Three position vectors, each three-dimensional, all coupled together through the gravity terms on this slide. Every body feels gravity from both others simultaneously. The force on body 1 has a term from body 2 and a term from body 3. Same structure for all three. Nine coupled nonlinear differential equation, all changing together, all feeding back into each other. Poincare proved no closed form solution can exist for this system in general. Now here's what is quite peculiar. For over 300 years, everyone had assumed the three body problem was complete chaos. No structure, no pattern, total disorder. Then, in 1993, a mathematician named Chris Moore found a specific set of initial conditions where three equal masses chase each other around a figure eight. This example over here, perfectly repeating forever. He hadn't solved the general problem, but he had found a tiny pocket of perfect order hiding inside the chaos. Since then, mathematicians have found about 20 families of these periodic solutions. They have names: the figure eight, the butterfly, the moth, the yin yang, etc. What you're watching right now is all of them together. In every one, three bodies trace a path, and after a fixed period t, their positions and velocities return to exactly where they started, forever. These solutions are remarkable because they are exceptions. For a generic set of starting conditions, the three body problem is chaotic and the trajectories never repeat. These 20 families are islands of perfect mathematical order inside a chaotic ocean. There's one more exception, and this one has very practical consequences. Euler and Lagrange found five special configurations, the Lagrange points, where a third small body can stay fixed relative to two large ones indefinitely. L1, L2, and L3 uh, are semi-stable, and they lie along the line connecting two main bodies. A nudge and the object drifts, needing the occasional correction burn. L4 and L5 are 60 degrees ahead of and behind the smaller body in its orbit. They are fully stable. Look at this map of our solar system. See these large green swarms of leading and trailing Jupiter. These are actually the Trojan asteroids. Tens of thousands of them permanently parked at Jupiter's L4 and L5 points. Not held there by anything physical, just by mathematics of gravity and three body problem. And the James Webb Space Telescope, right? It sits at the Sun Earth L2 point, 1.5 million kilometers from Earth, perfectly stable. Even in a chaotic system, there are pockets of perfect mathematical order. That was my part of the presentation. Now I'd like to hand it over to Arham.
Yeah, I'll start presenting my screen now. So, is my screen visible?
Yes.
Okay. So, now that you have understood a bit of how the calculations are done and how to implement them, so let's look at some real world examples of how we use them. So, most of us might have studied this in our JEE days, and even if you have not, there is a link to the derivation for this in the resources part of this page, and we'll share this page later with you. This is the Tsiolkovsky rocket equation, and if you want, you can try deriving it on your own. You just have to write force equal to dp by dt, and you have to treat momentum and velocity both as variables. So this is the the main rocket equation. Now, once you know this, how do you actually go from one place to the other place? So let's look at a real world example. We have the trajectory of the InSight probe from NASA over here, which went from Earth to Mars. So I'll let it loop around again so you can see exactly how it goes. It starts out at Earth over there, and instead of going directly in a straight line, it uses a elliptical trajectory. So this is called an Hohmann transfer orbit, and we will be
Sir,
deriving this. Yeah.
the screen is not visible.
Oh, it's not visible.
It is visible, but
Yes,
can
sir.
you reshare it?
Yeah. It is. Is it visible right now?
Yes, it is.
I think
But
it is
it's
problem from my end.
it's not
Yeah.
visible to me. I don't know why.
Can you rejoin the meet?
I did actually. I just rejoined it.
Hmm. I mean, right now I don't think we can do anything. I'll just for now I'll continue. The resources will be shared to you later, anyways. So, is the animation visible to most of the people right now?
No.
Yes.
Yes.
No, sir.
It's not visible to some people and it's
No,
visible to some people.
no.
Mm. Let me try one thing, just a second. Yeah, so is the screen visible first of all?
No, sir.
No. It's not.
No.
No.
Maybe you could try rejoining it.
Yeah,
Is
I'll
the
try to
screen
give
not
you one.
visible?
Uh, can everybody for whom the screen is visible raise their hand? So it's not a problem on my end, then I think it's a problem with other people. Yeah, so right now I don't think we can do anything. We will just share the resources after the presentation is over. Okay. So I'll continue. Um, this was the animation that I was showing you. So as I said, this is a Hofmann transfer orbit, and you can look in the animation. It goes from a smaller to a larger orbit or a larger to a smaller orbit, depending on our case. And instead of constantly burning fuel the entire trajectory, it needs to give a burn only twice, or at least theoretically. So it first gives a burn to go into the ellipse. I'll show you in the next slide. So the first, if it's going from orbit number 1 to orbit number 3, it will give a burn at the smaller orbit and move into the number 2 orbit, which is the transfer ellipse. And then as it comes near the third orbit, it will give a burn to slow down and enter the third orbit. So this is the basic idea behind the Hoffman transfer orbit. So here we'll see how it's derived, and the three things we can derive for it: the velocity changes that we require, the burns, the time required, and the angular separation at the start of both the planets. So we can see that this here is the energy of an orbiting body orbiting a much larger body. We can divide, but we can solve for velocity, and we'll get this equation: v square equals to mu a, where mu is gm. And at the perigee of the transfer ellipse, this is the old velocity and this is the velocity that we want to go into the transfer ellipse. So if we just subtract one from the other, we'll get delta v, which is the change in velocity that we want. And similarly at the apogee, we can calculate both the old velocity inside the transfer ellipse and the new velocity that we want inside the new orbit. So this is how we get delta v. The time required, so for a theoretically ideal Hoffman transfer, it will always end up 180 degrees opposite to where it started. So from Kepler's third law, we know that this is the formula for time, which is t square equal to 4 pi square a cube by mu, where a is the semi-major axis of the ellipse. And we can just input the values into the time formula and we'll get the time. So if we take an example of Jupiter, one Jupiter Earth, one Jupiter year is roughly 12 Earth years. From there, we can calculate that the radius of Jupiter is roughly 144 to the power one third radius of Earth. Putting that into the formula, we'll get 2.756 years roughly to go from Earth to Jupiter in the ideal case. And since we can back calculate the angular velocities of both Earth and Jupiter, we just use them to calculate the initial angular separation by just subtracting it from the angle moved by both the bodies during the transfer. So for example, for Jupiter, that would be roughly 97.3 degrees. So does anybody have any questions regarding this? If not, I'll move forward. Okay, so now that you have seen this, does anybody know which is the furthest man-made object in space right now? The ones which are the outside the
Yes, sir.
heliosphere.
It is Voyager. It is Voyager.
Yeah, yeah, that is correct. So Voyager did not use just Hoffman transfer. So one extra, will show you the trajectory of it. This is Voyager 2. Uh, I'll let it play again. So it goes from Earth and it moves along all the planets. So one special thing you'll see here is that it's changing angles drastically when it meets some of the planets, and that is called a gravitational slingshot maneuver. So instead of burning fuel for large speed gains, it uses the gravity of the planet that it is passing by, and so the fuel is conserved and it can gain huge amounts of speed without burning any fuel. So you can see that in the planet frame, the incoming velocity of the or spacecraft and the outgoing velocity of the spacecraft will be equal, and that means that the maximum velocity theoretically gained will be 2 times the velocity of the planet. So that will be in this case where this is a very ideal case. It is approaching the planet head on and then leaving in the direction of the planet. But what if we have a case like this where we know the initial and final angle and we want to calculate the change in velocity after this maneuver? So that's what we'll do now. So in the planet frame, we know that the kinetic energy is conserved, and we will assume that the mass of the planet is much bigger than the mass of the spacecraft. So the planet will have negligible change in momentum and kinetic energy compared to the spacecraft. So here we can conserve the kinetic energy in the planet frame, where vi dash and vf dash are the initial and final velocities of the spacecraft in the planet frame, and we convert those to solar frame. We do the dot products and we'll get a quadratic for the final velocity. And if we solve that, we will get this expression for the final velocity. And one interesting thing is that some we can use this for gravitational braking also, where we are too fast to go into the orbit, but with using the gravity we can slow down. So the negative sign here is ignored because magnitude cannot be negative. And over here we can see that if vf is smaller than vi, we can have gravitational braking, and we can square both sides and solve to get this condition where cos theta f is smaller than cos theta I as the condition for gravitational braking. I'll show you another interesting animation. So this is Voyager 1 as it flew by Jupiter, and interestingly enough, doesn't it look like the typical description of atoms we have in the textbooks? So the, we can use that because electrostatic and gravitational forces are pretty similar in their formulae. So we can use the formula of Rutherford scattering to calculate as well in case we don't know the final angle. So if you only know the incoming speed of the spacecraft, we can use this. And I won't be going into much details about this one because it's the match is slightly more advanced. This will be shared to you. So if you want to, feel free to, because there will be three different solutions in this PDF. So when the planet is coming in, we have the initial angular momentum and the initial energy, and we can conserve both of them to find the distance of closest approach of the spacecraft to the planet. And we can use this diagram and we can see that the orbit is symmetric about the closest distance of approach line, and we can use that to see the change in momentum and as a vector form do an integral, again use angular momentum, and we'll get the deviation angle. So using the deviation angle we can calculate the final velocity in the solar frame also. So is again, is everybody with me? Did everybody understand for now? Nobody has any questions. So you might be wondering that all of the maths is fine and all, but how do we make computers actually solve this, and how do you approach that? So for that, I'll call back Ishan again to. Uh, some people are raising their hands, so I don't. Do you have questions, or were the rest from before only? Anindya? Okay, Anandya, Rohit, Ankit, Siri. If you don't have questions, I'll just give it back to Ishan.
Is my screen visible?
Yeah.
Yes, sir.
Yes, it is. This is visible.
Okay. So Aram just showed you real missions being navigated numerically. Let's understand the math behind the numerical solutions that we were discussing earlier. The simplest method is the Euler method. Developed by Leonard Euler in 1768, and here's the derivation of why it works the way it does. At each time step, we compute the gravitational acceleration from wherever we currently are. We use that to update our velocity and the new velocity to update our position. For a solar system simulation running at 1 hour steps across millions of years, you're basically doing this billions of times. It sounds robust, but trust me, it isn't. Let's take a look at what this problem looks like mathematically. So we're basically trying to approximate this curve right here. The gray line is the exact perfect path. We use the Euler's approximation method to approximate this graph. As you can see, the approximation isn't that perfect. Because the Euler's method relies on straight line tangents based on the current slope, it constantly overshoots and undershoots the peaks and valleys. The error stacks, and over time it drifts further and further away from actual curve. Now I can make this approximation better by reducing the step size. But what it in turn does is increase the number of these dots, which basically represents the number of iterations that our computer has to perform by a lot. So basically, it decreases the efficiency. When we apply this stacking error to an actual orbit, this is what happens. This dashed line is the actual analytically calculated orbit, and when we use Euler's approximation for this, as we notice, the planet starts to slowly drift away from the actual star or the actual orbit. This technically gives it some extra energy, which obviously there isn't. So this is not that good of an approximation. The error in Euler's method is proportional to the time step, which is delta t. To halve the error, you must have the time step, and which will double your calculations. What you actually want is a method where the error drops off much more as we halve the step or we halve delta t. So let's say if we find a method which is proportional to delta t to the power 4, halving the error will then result into halving the delta t would then result the error to drop by 16 times. So this is exactly what the RK4 or the Runge-Kutta-4 method does. Instead of one tangent, RK4 samples the slope 4 times within a single delta t and then takes a weighted average. So this results in the error to be directly proportional to the delta t's fourth power. Let's take a look at actually what happens in RK4 method. This is the graph where the x-axis represents the time and y-axis represents our position. Our goal here is to approximate this curve using the RK4 method. We have obviously amplified the scale much more, so it's easier for us to see. Instead of just Ti and Ti is the initial time, instead of Ti and Ti plus delta t, we have additionally introduced Ti plus delta t by 2 to our graph for the RK4 method. Let's take a look at an actual example using an interactive simulation. This is a graph of dy by dx is equal to y. And if you actually perform the math, it's basically e to the power x. Our goal here is to approximate this graph using the RK4 method. I'll show you what actually happens. We'll first introduce the vector field, which is basically the tangents at each point. So the tangent dy by dx is just y. So we get this as a vector field. Now, we start with k1. K1 starts here, and then with the slope of k1, we extrapolate it up to the midpoint and find k2. We then use this k2 to find k3 by extrapolating k2 from the initial point up to the midpoint. This is our k3. Now we finally use this k3 to get k4 at the endpoint. Then, using the Taylor's method, we take a weighted average or a weighted mean over all these values to finally get this, which is our first approximation. I have magnified the scale by a lot for you to see, but you get the point. This is how the RK4 method works. RK4, if let's take an actual example of how efficient the RK4 really is as compared to Euler's. If Euler needs 1 second time step to stay stable, RK4 gives you the same level of accuracy at 10 seconds even, 10 times fewer calculations. Every serious physics simulator uses this. And remember the simulation that we saw earlier and all the simulations that Aram had shown you, all of them are based on the RK4 method. For all physics simulation, for all practical physics simulations, we use this method because this is very much more efficient than Euler's method or any other method. That's why it's also called the gold standard. If you want to go deeper on RK4, there is a Wikipedia link in the resources slide. Back to Aram for the final act.
Yuvraj, you just raised your hand right now. If you have, do you have a question?
Yes, I actually could not really understand a lot about what the RT4 method was. Could you just explain it a bit more, please?
Yes. So for all the simulations, all for all the mathematical simulations of our three-body problem and even the two-body problem, we need the computer to approximate the solutions because we do not always have an analytical solution present with us. So that's basically RK4 is just a method for a computer to do physics.
Yes, because in our lab we were using the Euler method mainly,
Yes,
and
Euler's method is okay, but for small scale simulation. For actual billions and billions of calculation, which you won't be able to do on your computer, of course, even for the supercomputers, you need a much more efficient method. So RK4 provides that.
all right, thank you.
Okay. So I am assuming my screen is visible for at least the people for it was visible. Karthik raised his hand.
Yes, am I audible to you?
Yeah, yeah.
Yes.
The RK4 approximation thing is something similar to what we actually do in MATLAB. So why is it you take this number 4 as approximating 4 means, and why not any other number? Let's say 3 or 2.
Uh, yeah, Ishan, go ahead.
Yeah, you need a perfect balance between accuracy and complexity. So that's why RK4 is the gold standard. It provides answers with well enough precision and not that complex.
And also, there is a long theory behind how these numbers were chosen. I mean, there is a whole deep dive you can do into RK4 if you want.
Mm-hmm. Yeah. Thank you so much.
Yeah, no problem. So, for the people for whom my screen is not visible, I've shared the website link in the chat. So, if you want, you can follow along there as well. I'll continue. So, now we come to extreme gravitational phenomena. And the first one that we see is tidal forces. So, uh, almost everybody knows about tides that we'll have high tide twice in a day, low tide twice in a day. But have you ever wondered why is it twice in a day? Why not once? Because the moon is only on one side of the earth. So, I mean, does anybody know the answer to this question?
Because the moon is tidally low.
Sure, but that doesn't answer why there is a bulge on the opposite side of the earth as well. Does anybody else have an answer, or should I continue?
The rotational period of the moon is equivalent to 1 day.
Uh, it
I
is
mean, like,
equivalent to 1 day, but
and like we
yeah,
see the high tides on the like direct side and the opposite side. So it's like the
yeah, but
opposite and direct side will be coming on the same.
no, but that is my question. Why is there a high tide on the opposite side? The moon is not pulling from this side, right?
Is the combined effect of moon and sun?
Uh, Not exactly, because even if the moon and the sun are on the same side, you will still have a high tide on the opposite side. So, I mean, I'll explain in the next slide. So, we can draw all the vectors of all the forces here, and the blue arrows are the vectors of the forces. Suppose the moon is at the point S, so the blue arrow shows the magnitude and the direction of the force at that point, and at O you can see the blue arrow. So what the red arrows are is that at every point the force at O is subtracted from that point. So what you can see is that when we subtract it, there is an opposite force on the far side of the earth. Now that is what causes the bulge, but that I don't think that is a satisfactory explanation. So I'll try to explain it. The closer side is obvious because the gravity is pulling much harder on it than compared to the other side. But what happens on the other side is the center of the earth is being pulled away stronger than the actual water on the opposite side of the earth. So it's trying to catch up, but so it creates a bulge there. Is that more intuitive? So that's why there is a bulge on both the sides, because water is being pulled on one side and on the other side the earth is being pulled away from the water, is the way I like to imagine it.
So is it the
So
sun pulling it?
no, it's not the sun pulling it, because the sun and the moon can be on the same side sometimes. The moon the moon has the major gravitational effect for tides. Sun has a lesser of an effect.
Or is it just due to the centrifugal force there?
Yeah, you can kind of think of it like that. It's like the centrifugal force. Yeah.
Right, because it's spinning, so it would go outside like it usually does.
Oh no, you mean the because of the rotation of the earth,
Uh,
or the revolution of earth and moon
uh,
around their barycenter?
yes, that one.
Yeah, so that is kind of it. Yes, you're on the right
Is it
track.
because of the inertia of the
Because of the inertia of the.
water? Like because the water was there at the position and it resisted to move alongside the earth as earth was
Yeah,
pulled from
that
the
is
opposite.
exactly analogous to the centrifugal force thing. Because it's rotating around, it's being thrown away more. Centrifugal force is, as you know, a pseudo force. So in reality, the Earth is being pulled inside with more force compared to the water out the outside. So that's why it has a bulge over there.
Yeah.
Yeah. So this is a very cool looking example of a spiral galaxy and a smaller companion showing tidal forces. It might not be obvious in this photo, but the smaller galaxy is being deformed by the larger galaxy, obviously. And this is a very special example. So, have you ever wondered that why don't Saturn's ring just clump up and form other moons? Why do they always stay like this? Why are they always dust, and why don't they just collapse into the planet or maybe form moons? So, uh, this brings us to the next topic, which is the Roche limit. So the Roche limit is where the tidal forces become stronger than the self gravity of the object. So what happens is when the dust enters that region of Saturn, it can't hold itself together anymore because the tidal forces are stronger than the forces holding it together. So you can see an example here. When it is far away, both the bodies are perfectly spherical. As it comes closer, it gets a more oblate shape, which causes it to deform. As it enters the Roche limit, it starts ripping itself apart, and then it starts orbiting the planet and it becomes rings. So it was theorized that the Saturn's rings are a moon which entered the Roche limit and broke apart. So that is one of the major theories. This is a very cool simulation of the Roche limit. You can see. So yeah, that was a very, you can see here the rings are getting formed, it becomes rings. So there is another example of Roche limit that happened. Has anybody heard about the comet Shoemaker-Levy 9? I mean, if you have heard and you know why it's special, you can tell us. Okay, so I'll tell you. In 1992, the comet, which orbits around Jupiter, in 1992 it entered the Roche limit, and it fragmented itself into 21 different parts, and it looped around and it slammed into Jupiter. And this was very exciting because for the first time astronomers were seeing two celestial bodies slam into each other, and it was a very good opportunity to study the atmosphere of Jupiter and all. So next I'll show you the trajectory of the comet. So it starts from 1992. There are actually many pieces there you can't see because they're very closely stacked together. You'll be able to see as they turn around. Yeah. So these are the impact spots. This is just the moon of Jupiter. The dark spots you see below are the impact spots. This is the photo taken by the Hubble Space Telescope in ultraviolet light. So this is one of the things that Roche limit was used for. So I mean, do you have any questions regarding the Roche limit? Cool. So, one interesting thing about this was that when the impact happened, it was actually facing away from us. So we were lucky that some of our probes were on the opposite side of Jupiter at that time, and also because Jupiter turns very fast, we were soon able to see the impact spots. So now that we've learned all this, let's learn about an exception to Newton's gravity. Because we thought that because we had now gotten the theory of gravity, we should be able to calculate orbits of all planets and all. But so Mercury was a very special case because no matter what things we considered, with Newton's gravity, we weren't able to solve for the perihelion precession of Mercury, which is the orbit of Mercury is a ellipse, and the orientation of the ellipse keeps changing every year and every orbit. So this is what it looks like. It's not necessarily as drastic as this. Every century it changes about 53 degrees, if I'm right. And so the Newton's theory was around 43 arc seconds off of the actual angle. So humans did what humans do best, and because they weren't able to satisfy everything, they came up with a new theory, which is Einstein's theory of gravity. So there is a popular misconception that Newton's theory is just that for gravity is a natural force, and Einstein's theory says that it's the curvature of space-time. The truth is that Newton's theory can also be written as a curvature of space, but the major difference between both is that Einstein considers space-time as one singular object, and Newton's theory has them both as different objects, which causes some slight changes in the maths, and that is what creates the small discrepancies. So in Einstein's theory, we know that the space is warped. You can see here. Now, this is the conventional image that comes to most of our minds, but in reality, space is 3D, and this is what the warping. I mean, this is also not what the warping look like, but this is closer to what it would look like if we could visualize it. And so now comes the major question: if mass follows the space-time curvature, so mass travels on straight lines in space-time, and these straight lines are called geodesics. Now, if it is traveling straight lines and it only looks like it's curving because of the space-time curvature, we were also taught that light follows a straight line always. So does light also curve with space-time? And the answer is yes. So these paths, the straight lines on curved surfaces are called geodesics. So you can see the visualization here. Imagine there is a heavy body here, which is curving space-time. Light will come from this light source. It will travel. Travel a straight line on this curved surface, it will look curved to us and it will then enter our eyes. So it would look to us as if light suddenly decided to curve over there for some reason. And in special cases, we get rings like this because a light source is directly behind a massive object, and it becomes a ring around it, and we can see it like this. And this is a very special example because it looks like a smiley, and people call it the Cheshire cat as well. And everybody nowadays knows this black hole, which is also another prime example of gravitational lensing. So what happens here is it looks like it has two perpendicular rings of matter and light, but in reality it is only one flat ring. What happens is that the part behind the black hole, the light from that gets curved up and into our eye, and the part below gets curved from the down and into our eye. So it looks like it has two perpendicular rings. One of my seniors has actually made a very good simulation of this. You can see the gif here. As the black hole turns, you will be able to see. I'll let it play out for a bit. Yeah, it'll start again now. And so now, as it turns, you'll be able to see the lensing around the black hole. From first, we see only a flat disk, and now it becomes two perpendicular disks, so which is very cool. So yeah, that was all from our side. You can feel free to ask us any questions. We'll be willing to answer.
Yes, can I?
Yeah, sure.
Okay, so I was reading the model that you sent, and can you please explain what an Einstein ring is again?
So an Einstein ring, I'll show you the image again. So okay, imagine there is an object. Now what I've told you is that light also bends because of the curvature of space-time, and curvature of space-time also causes what we perceive as gravity. So imagine there is a large object and it's very massive. Behind it is another object which is emitting light. So as light goes from that object to us, it will go all around the object, but the light will be curved back down into a focal point, which is our eye. So it will look to us as if it is coming in a ring. So if we go back to this image, this is only 2D, but imagine it in 3D. Like I said, the perception is like this, but in reality it will be more like this. Here, imagine the light rays are emitted in all directions as once. So the rays coming to us will be curved like this and this and this, and it will form a ring. Does that make more sense?
Does it have
I
anything to do with interference?
No, I think interference is a completely different phenomenon. What exactly do you mean by interference here?
Like, what if the light is coming from every direction and then it bends, and due to interference, the ring becomes more visible or so? I was just curious.
No, I mean interference might be involved, but that is not the reason that we see Einstein rings. Not the primary reason, at least.
Yeah, those are the Newtonian rings, I think, right?
I'm not really familiar with that actually, so I can't comment.
Uh, that is.
Like, how does the brightness of the Einstein ring vary?
It depends on the number of rays that we can perceive that travel into our eyes and how direct they are. How, like, for example, if they're at an angle to us, they'll be less bright. Yeah, Adrita, you can speak.
Oh, no, I just did it mistakenly. I'm sorry.
Yeah, okay. Does anybody else have more questions regarding any part of the entire presentation?
Just one thing, you were showing us some simulations earlier from a GitHub website, I think.
This one. Hang on. This
I
one?
actually cannot see. I cannot see your screen actually.
Oh yeah.
But I'm saying that. Could you please share their website as well in the chat?
It's shared in the PPT, the resources link. It will be there. The black hole simulation. I'll share it in the chat. I'll
Ah,
share the GIF that I have on screen right now. But if you want, you
okay.
can have a look at the GitHub thing from the website as well. It's in the links.
Okay. Do share the giveaway. I couldn't
Yeah,
see that.
I've shared the GIF in the chat.
Okay, thank you.
If nobody else has any more questions, then we can end the meet.
Just one thing. When will the next session be?